This example is special because it's a proportion. What is a proportion? A proportion is two fractions with an equal sign between them. When we have a proportion, we can solve it by cross-multiplying. Now, this only works with proportions, so you want to be aware of why it works so that you don't use it in the wrong places. One of the common places that students will do this when it shouldn't be done is if they were multiplying these two fractions together. This does not equal 1 times x plus 1 times 2 times x minus 1. So that's just something to watch out for. You don't cross-multiply when it comes to multiplying fractions, and the term cross-multiply can seem confusing. When we multiply fractions, we multiply them straight across. So if we were given 1 over x minus 1 times 2 over x plus 1, we should multiply numerators to numerators and denominators to denominators, right? So you don't just cross-multiply in general, but you cross-multiply when you have a proportion, which is one fraction equals another fraction. Now let's talk about why cross-multiplication works in this scenario. We've previously solved equations involving rational expressions by finding the LCD and then clearing the fractions. So let's see how that would work here. So what is the LCD? Since there are no common factors for either one of my denominators, it'll be the product of the two denominators. So when I take the left side of the equation and multiply it times the LCD, you can see that the x minus 1 factor is going to cancel out. And when I multiply the LCD onto the right side of the equation, you can see that the x plus 1 factor is going to cancel out. So let's just work it out. And I'm going to go ahead and put some parentheses around these just to make them look more like quantities. And so notice this x minus 1 and this x minus 1 go away. This x plus 1 and x plus 1 go away. So now the new equivalent equation in simplified form without any fractions involved for the first term, that becomes just x plus 1. And on the right side, we have a 2 times quantity x minus 1. So we get this. So notice what would happen if we cross-multiplied. If we cross-multiplied 1 times x plus 1 like this, then we would have the left side of this equation. And if we multiplied 2 times x minus 1, then we would have the right side of this equation. So it's a shortcut, and it works nicely. But you can still get here, obviously, by using the approach we've already been using, which is to find the LCD and clear the fractions. Now that we have this, we can continue simplifying and then solve for x. So I'll distribute the 2 on the right, and then consolidate all my variable terms together. And then get the x by itself. And so now I have x equals 3. So my proposed solution set is 3. But we want to check to make sure that not only does 3 satisfy my original equation and make it true, but it also doesn't make my equation undefined anywhere. So here you can see if we plug in 3 to both sides of the original equation, we have a result of 1/2 equals 2/4. And since 2/4 can reduce to 1/2, this is true, and we're satisfied with our solution set. In this example, we're going to have to find the LCD to clear the fractions, and this denominator here is already as factored as it's going to get, and so is this one. But the 9 minus a squared can be factored, so let's go ahead and do that first. Now 9 is a perfect square, which can be written as 3 squared. And a squared is it's a perfect square. So this is the difference of squares, which has a special pattern for factoring 3 minus a times 3 plus a. Now, if I rewrite my original equation as 12 over 3 minus a times 3 plus a, and then just rewrite the other terms as they are, now I'm ready to multiply through by the LCD and cancel out all my fractions, cancel out all my denominators, in other words, clear the fractions. Now, I can go in and write the LCD into each numerator. This is equivalent to multiplying both sides by the LCD and then distributing it on the left side where I have 2 terms. Then I can go ahead and cancel out common factors from each term. And rewrite the simplified version. Oh, I forgot to cancel this out here. And the simplified version of the equation without any fractions is 12 plus, let's go ahead and distribute this 3 here and get 9 minus 3a equals, distribute the 2 here, 6 plus 2a. Now what you'll start noticing the more you do this is that you can probably get it done without as much writing once you're experienced enough. So I'm just going to show that in another slide here. I thought I duplicated it, but not yet. Let me try that again. All right, there we go. And we'll go ahead and clear the ink here. Maybe not all of it. Let's erase just this step here. Okay, so once we have this rewritten as 3 minus a, which is also a denominator of one of my fractions, and 3 plus a, another denominator of one of my fractions, I can see what's going to cancel out and what's going to be left for each one of my fractions. For instance, for 12, when I multiply by that LCD 3 minus a times 3 plus a, nothing's going to be left. Everything's going to cancel out. But when I multiply that LCD, and let me write it over here, when I multiply that LCD to my second fraction, I can already see that the 3 plus a is going to go away, but the 3 minus a is going to remain. So I can just rewrite this that way. And for the 2 over 3 minus a, I know that the green factor 3 minus a is going to cancel out, but the 3 plus a, the blue factor, will still be remaining. Now that I have my new equation without any fractions in it, I can go ahead and simplify and solve for the variable. So I'll go ahead and combine like terms. So 12 plus 9, that's 21. Now that all of my like terms are combined on each side of the equal sign, and there's no other simplifying to do on either side, I can begin moving things across the equal sign, doing inverse operations to get a by itself. The first thing I'll do is move these 3a's over to the right. That'll zero them out on the left, so all my a's will be on one side together, and they'll all be positive, which is why I chose to move them to the right rather than the left. I can also move all the constants to the opposite side, away from all the variables. So I will zero them out on the right and consolidate them on the left. So my resulting equation is 15 equals 5a. The last step is to invert the multiplication that's happening here between 5 and a. The inverse of multiplication is division. So this will cancel the 1. Then I have a equals 3. So my proposed solution set for a is just 3. But I need to check it, because right now I don't know for sure if 3 is going to work until I plug it back into the original equation and make sure that the equation is satisfied, that it's true when I plug in 3 for a, and also that it doesn't make any of my fractions undefined. You may have already noticed that when you plug 3 here, you're going to get 3 minus 3 in the denominator, so you'll have 2 over 0, which is undefined. So I can see clearly that this is going to be a problem. So this is the result we get when we plug in a equals 3, and we actually got it twice over under the 12 as well. So now I know that 3 is not a valid solution. And since it was the only one that I had as an option, there is no solution. So what I would say here is, but a equals 3 makes the equation undefined, so there is no solution. know, if I had more than one option and only one of them makes everything undefined, then I would still have a solution to give. But since 3 was the only one and it doesn't work here, then we have to say there is no solution. That's the answer. So this is the first example we've seen from this set of examples that we have an invalid solution. And so we just want to take a moment to remember that this is why we are even more sure to check our answers, because we want to avoid giving an answer that seems right, especially if we've done all the work right. We did all the work right. We got a equals 3. If we check all our work, it's all correct. It's not that we made a mistake, it's just that it's not a valid solution. Now, another way that you can avoid giving invalid solutions that I've shown before is you can start from the very beginning thinking about possible invalid solutions so that you can avoid them. So I still would want to factor and rewrite my denominator as a first step. And then I would look at all my denominators and say 3 plus a should never be allowed to be 0. Therefore, if I solve this statement for a, I get a should never be allowed to be negative 3. Same thing happens when I do 3 minus a. Say, hey, don't let that denominator ever be 0. Well, I can actually do this more efficiently if I say 3 minus a not equal to 0. I can actually add a to both sides. So I have 3 should never be equal to a. So these are two invalid solutions that can't be part of my domain. So the domain should be a is a real number where a is not equal to 3 and a is not equal to negative 3. That's if I was finding the domain, but we don't say it in that way in this circumstance because we're talking about an equation. But it's a good reminder for when we did look at it as finding the domain. All right, let's look at another example which requires some factoring again to find the LCD so we can clear the fractions. We'll go ahead and factor this first. Lead coefficient is 1, so I know my two binomials will start with x. The last term is positive, so I know the two signs in my binomials will be positives or both negatives. They have to be the same, either both positives or both negatives. And the middle term being positive means they will both be positives or pluses. All right, now I look for two numbers to multiply to give me 10 and add up to give me 7, so that's 2 and 5. Now I'll find my LCD. So my LCD will contain common factors. So I have x plus 5 here and here. Common factors get written once, or once for each time you can pair them up with any other denominators factor. And then the x plus 2 might be common. I didn't factor everything that I could factor. I almost forgot that I should also be factoring here, because there is a 3 that's common there. So I can take out the 3 and notice that I get x plus 2 as a quantity. So now that's common with this. So that'll be part of my LCD. And now that I've covered all the common ones, I do have one uncommon factor of 3. Okay. Now, when I multiply that LCD to all of my terms, things are going to cancel out, and I'm going to use color coding to show how that canceling out will happen. I'm going to do this in a more efficient way. Than rewriting everything and multiplying. I don't want to write out multiplying the LCD every time. There is a more efficient way. I don't recommend doing it this way, though, until you've already done it the long way. Several, I would say many, many times, till you really get the concept. Then you can start saving yourself some writing steps, because these can get a little lengthy. So I would at least write x plus 2 over the factored version of that denominator. Just rewrite all your fractions so that the denominators are in factored form. It helps to see what cancels a lot easier. And I like to put parentheses around my quantities, even if they don't need them there. Then I look at my LCD, and I know that when I multiply the first term by this LCD, the x plus 2 is going to cancel here. And also the x plus 5 is going to cancel. The only thing that won't cancel is the 3. So I can rewrite this term as 3 times x plus 2. For the second term, notice the x plus 2 is going to cancel and the 3 is going to cancel. So the only thing that's not going to cancel is the x plus 5. So I can write the 1 times the x plus 5. And I'll bring down my minus sign and rewrite this part. We see that the x plus 5 is going to cancel, but the 3 and the quantity x plus 2 will not. So I have the 1 times 3 and times x plus 2. So now I'll distribute and simplify, combine like terms, and then start solving. So distributing 3 times x plus 2, I have 3x plus 6 equals x plus 5 minus 3x, so that's a negative 3 multiplied times x, and then negative 3 multiplied times 2 gives me negative 6. Then combine like terms on each side of the equal sign so that the x and the negative x become negative 2x, and the 5 and the negative 6 become negative 1. Now that everything is simplified on each side of the equal sign, I'll go ahead and start consolidating all my variables to one side, choosing to go to the left since then everything will be positive. And I can also consolidate all my constants to the other side, so now I have 5x on the left is equal to negative 7 on the right. And when I do my last step, inverting the multiplication of 5 by doing division, I have my proposed solution of x equals negative 7/5. So we'd like to check that solution by plugging it in. Okay, now we should really check this solution, but it's going to be a lot of long drawn out work if you're doing it by hand. Now you can rewrite x as negative 3.5, or is that right? What is negative 7 divided by 5? See, 1/5 is 0.2, and 7 times 2 is 14, so it should be about 1.4. Negative 1.4. So then you could go in and replace x with negative 1.4, and then use your calculator to help you simplify each part. And I would just work with each part, each term individually. To see what each of these pieces equals, then, first work this out, get the approximate amount. If it's a decimal that doesn't terminate or repeat, you can abbreviate it, you can round it to do a whole bunch of decimals out. And then same thing for each piece over here. Get your approximate amounts in decimal. Put a lot of decimal places. If your left side does turn out to be about the same as your right side, you can feel pretty safe that your answer is correct. I still recommend actually putting in the fraction in its exact form and trying to work it all out, because it'll give you practice that's really good for you, because working with fractions is an important skill. And so I definitely think you should try it, but let's be real. If you're working on a test question especially, and you're trying to check your answer, if you're going to plug in negative 7/5 into all this and try to simplify it, it's going to take you a long time. There's a lot of places that you could make a simple mistake and then have everything be not working out correctly. You can waste a lot of time doing this. So I recommend using your calculator to help you with this. Now, the other thing that we're concerned about is not only does it make the equation true, but does it make any of my denominators 0? Because I don't want 0 in any of my denominators. So remember, we worked out before how we can look at an equation even before solving it and determine any problematic x values so that we don't include them in our final solution by mistake. So let's do that step, okay? Let's find out, let's identify any invalid solutions that are possible or could come up. Or if I should say it this way, if any of these come up, I will know to not allow them to be part of my solution. So we're going to identify invalid solutions, and if negative 7/5 is one of them, then we'll know that this is a no solution. example. So we've already factored out our denominators. So let's write those with their factored forms. So remember, this was x plus 2 and x plus 5. This one came out to be 3 times x plus 2. So all we need to do is make sure that none of our denominators ever equal 0. So x plus 2 can't be 0. X plus 5 can't be 0. And that'll do it. So x cannot be equal to negative 2, and x cannot be equal to negative 5. So neither one of those are the answer we had. So if I was in a pinch, I might not go through all the work of checking the negative 7 over 5, but at least I would make sure it's not one of the possible invalid solutions. All right, so in summary, to solve an equation containing rational expressions, step 1, clear the fractions by multiplying both sides of the equation by the LCD. Step 2, simplify both sides of the equation and then solve for the variable. Step 3, check the solution, especially to make sure that there are no invalid solutions. Objective 2 in this section is solving equations containing rational expressions for a specified variable. So this kind of example is where we have more than one variable, and they're telling you to only solve for a certain one. So what that really means is just to get A alone. Now I'm going to approach this the same way I've done with other examples. I'm going to simplify this by multiplying through by my LCD. So what is the LCD? The LCD here is A, B, X. So I will multiply all of my equations by ABX and see what cancels from each term and rewrite it. So we first have the A, I'll do that in blue, the B in green, and the red, well, I'll leave X purple. All right, so when I go to rewrite this after multiplying through by the LCD, the only thing that's going to be left after the A's cancel is B times X. For my next term, I have a 1 there. I had a 1 also here. I guess I'll just write it first to be thorough. For the next term, the 1 in the numerator, the B's are going to cancel out, and then the A and the X will be left over. Then we have the equal sign and another numerator that's 1. And when I multiply 1 over x by the LCD ABX, the x's are going to cancel, and the A and the B will be left behind. So I can get rid of all the 1's so that I just have BX plus AX equals AB. And I might want to leave the A in a different color just so I can remember what it is that I'm trying to get all by itself. I'm solving for A here. So now I'll combine any terms that have A's together. So I'm going to subtract AX from both sides. That'll zero this term out. So then I'll have BX is equal to AB minus AB minus AX. Now that the A's are all together on one side and there's no A's left on the other side, I can factor out an A from these two terms. And now to get a by itself, all I have to do is invert the multiplication of the quantity b minus x. I guess I'll write that in a separate step just so that it's more clear. So now I have bx equals a times b minus x, and I'm going to divide both sides by the quantity b minus x. So that this cancels to 1, and then I just have a equals, blue a, equals bx over b minus x. So that's my answer. A is now by itself. That's all I needed. Let's look at another one. Solve for r sub 1. Right, so just like we can use different letters to represent different variables, we can also use the same letter but put subscripts on them to tell them apart. So r is different than r sub 1, and both of those are different than r sub 2. If it helps you, you can do something like rewrite it as 1 over a equals 1 over b plus 1 over c, just using different letters to represent the different quantities. And then R1, well, it's in blue, R1 had been changed to B, so now I'm solving for B. If that helps you, there's no problem in doing that. Because sometimes with the little subscripts, things can get a little hard to write neatly, or you might confuse a 1 and a 2 somewhere. So I kind of like this. B is your R1, so you're solving for B. All right, so once I've done that, then I'm just going to find the LCD and rewrite everything. So the LCD is going to be A, B, C, and then for the first fraction, the A is going to cancel out, so B and C will be left over, and it's times 1, so I don't need to write the 1. Then when I multiply the LCD times 1 over B, the B's are going to cancel out, and I'll have just a C left over. Then for the last fraction, the C's are going to cancel out, so I'll have A, B. And now I can rewrite this so that only the B is highlighted in a different color. And then collect all the B terms together on one side. So I'm going to subtract the AB right here. Oh, there's something else I would do here, just to make it a little easier for the eyes, is I would rewrite this one so that it's in the same order as this one. Right, this was BC. I did not mean to erase that. Let me just rewrite it again. BC. So I'm going to write AB as BA. There's no problem with doing that because we know multiplication is commutative. What does that mean? That means something like 2 times 3 will give you the same answer as 3 times 2, right? 2 times 3 equals 3 times 2. the commutative property of multiplication. Right, so we can do that. And I only did that because I think it just makes it look more comfortable. And then I'm going to subtract BA from both sides because my goal is to get all the terms that contain the variable I'm solving for together on one side, and any other kinds of terms that don't have that variable on the opposite side. So now I have BC, oops, I meant to make that black, minus BA equals AC. Now I'll factor out the B, and divide both sides by C minus A. So my solution is B equals AC. Let me make sure I've got this right. And this isn't written quite right. I need to fix that. Okay, so now we've got it. So that's my answer right there, except for the fact that, remember, we used a placeholder for R sub 1. So I'll just change this back now to R sub 1. That concludes 7.5. I hope you got a lot out of it. Please email me questions and enjoy practicing math as always. Take care.